To find the volume of solid of revolution when the region is going to be revolved about the y-axis. Right. So we're going to use the shell method here. Before we go to the problem, we want to see what the volume of the shell. A shell is a hollow cylinder, and then we have this radius and the height, and the circumference here is 2 pi r. If we kind of cut open the shell here, if I'm going to cut open the shell and open it up, it actually becomes a rectangle, and this becomes 2 pi r, and this is the height. Of course, this is a 3D object, and then there is this very thin thickness or width of the rectangle, which is going to be dx or delta x. All right. So volume here would be 2 pi r h times delta x or dx or sometimes dy. Okay, we're going to see a demo and come back to this problem. So here we have the region R bounded by y equal to square root of x and y equal to x squared, and we're going to revolve it about the y-axis. Let's revolve it about the y-axis. So we have this object that is formed. This is going to be the solid that is formed. So this was the region, and it is going around the y-axis to form the solid and to find the volume of the solid. And the shell method is approximating the solid by infinitely many cylinders, the shells. So we have at every point xy on the graph, we're going to draw a cylinder starting from the innermost cylinder to the outermost cylinder. And then you add up all the volume of the shell, which will comprise the solid. So we can kind of see here that the actual volume and the approximation is the sum of the volume of the shells. Okay. So we kind of, all right, we're going to go back to the problem. So we have this, this is the region R, and it's going to be revolved about the y-axis. So first we will draw the reflection, and okay, so we have the region R, and we're going to draw a shell. Again, a shell has this volume. So we're going to draw a shell, take a point x comma y. Take a point x comma y on the graph and drop a line. We're going to draw a line parallel to the axis of rotation, and the line, the vertical line parallel to the axis of rotation, is going to revolve about the y-axis. So this goes about the y-axis. So a shell is formed like this. So this is at a point xy, and xy itself is a moving point on the graph. So this point could have been anywhere at here 0 0, or could have been at the right end. So we have shells from the innermost shell to the outermost shell, and we're going to continuously add all the volume of the shell. So volume of the solid is going to be continuous addition of all the volume of shell, which has the formula 2 pi r h dx. So the dx being that super thin width thickness of the shell, and then x starts from 0 all the way to 1, 0 to 1. And now we're going to give expression to the r and the h, and then integrate with respect to x. So here, this is the h value, this is the height of the cylinder, and this is the radius of the cylinder. So integral 2 pi, the radius of the cylinder is the horizontal distance, which is the x value, so x, and the height is the vertical height between the two curves, which is going to be the y value of the upper curve minus y value of the lower curve, dx. So we're going to rewrite this entirely in x, so we could integrate it with respect to x. I will pull the 2 pi outside. X times y value of the upper curve is the square root function. The lower curve is the x squared function. dx, and then ready for integration. So x times x power half minus x squared dx, 2 pi x power 3 by 2 minus x cubed dx, and then 0 to 1. And we're going to integrate this x power 5 by 2 by 5 by 2 minus x power 4 by 4, 0 to 1, 2 by 5 x power 5 by 2 minus x power 4 by 4, 0 to 1. And then when you apply the limits, we will get 3 pi over 10.